Hello everyone, welcome back. Today we're going to start Unit 3, which is going to focus on a field of math known as graph theory. Alright, so if you would like, you could read through some of the objectives and things here. I'm not going to read those to you. Instead, I'm just going to go ahead and start introducing what graph theory is and what it does for us. Alright. So in the modern world, planning efficient routes is essential for businesses and industries. Think industries and businesses like Amazon or FedEx or UPS, where they have to deliver packages to all kinds of different locations, and they need to find paths that are efficient and short and take the least amount of time, right? That's how they save money and keep the prices down when we do ship things. All right, there are all kinds of applications besides shipping, but laying fiber optic lines for broadband internet, social networking sites like Facebook use graph theory, all kinds of different applications in the modern world that use this. This is a widely applied field of mathematics. All right, it's actually a field of mathematics that started about 300 years ago based on a simple mathematical puzzle, which we're actually going to look at in today's lesson. All right, but it has exploded in importance in the last century because of the growing complexity of businesses and a global economy, and simply because now we have the computational power to really go through some of the graph theory algorithms that we're going to learn in this unit and quickly calculate those algorithms and we use those algorithms to find shortest paths, efficient paths, quickest paths, so forth and so on. And like I said, we'll see as we go through you'll see what I'm talking about. But a quick example that might help you understand is this housing development that we have pictured here. This is a housing development from Missoula, Montana. And as part of her job, the development's lawn inspector has to walk down every street in the development, making sure homeowners' landscaping conforms to the community requirements. So this person has to walk through all of these streets. She has to walk down every single street here, and she has to inspect all of these lawns. And she needs to do this in the quickest way possible. Maybe she wants to do it in the shortest way possible because she doesn't want to walk that far. But these are the kind of problems that graph theory are going to help us solve. You could also think of it as like an Amazon driver might have to deliver packages to several different houses in this housing development. Maybe an Amazon driver has to deliver a package here or here, here, and here, and he has to find a way to deliver to those 4 houses and find a path through this housing development that is quick, efficient, and cost effective. All right, so those are the kind of things that graph theory helps out these companies with. All right, so let's go through here, and what you're going to see next in this set of notes are a bunch of definitions. You can find this in the required reading as well. But I'm not going to read all of these definitions to you. I would make sure that you go through them. So if you come across a question and it asks about a loop, make sure you come back up here and read the definition for a loop so you know what they're talking about. All right, chances are if you read a problem and they give you a word or there's a word in the instructions that you don't understand, you're probably going to find it in this list here. All right, and as I work through our examples today, I'm going to talk about a lot of these in our examples. Okay, so here we go. Let's look at example 1 and get a graph going here. All right, so we have a graph. All right, and one of the first questions they ask us is how many vertices and edges does the graph have? All right, so these are 2 very important words, vertices and edges. All right, vertices are these guys right here, these points. So like F is a vertice, B is a vertice, A is a vertice, okay, or a vertex. All right, vertices is the plural. Edges are the line segments that connect the vertices. All right, so like this line right here going from B to E, that is an edge. E to A, this is an edge. All right, so like if I were to count up how many vertices this graph has, right? So let's make a V for vertices here, and I go through and I count 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 vertices in this graph. Okay, edges. All right, so we can go through and count up the edges. So we have 1, 2, 3, 4, 5, 6, 7, 8, and then we have this one down here, so 9, 10, 11, and 12 edges. Okay, so there are 8 vertices and 12 edges. All right, now the next thing it's asking is if the graph is connected. All right, so for a graph to be connected, this is one of those vocabulary words up above, you have to be able to travel from one point to any other point on the graph. So for instance, if I started at F or B or E, it doesn't matter. If I started at F, can I travel to every other point on this graph? So for instance, could I get to H? And I could, right? There's edges that connect me from F all the way to H. All right. There's an example of a disconnected graph when you go to read through the vocabulary terms. All right, so you can see what a disconnected graph looks like. All right, now in part C it says, what is the degree of vertex B? All right, so the degree tells us the number of edges that are connected to a vertex, right? So when I come up here to vertex B, I can see there are 1, 2, 3, 4 edges that go into vertex B. So its degree is 4. All right. Now it says if you travel from vertex F to H, is this a path or a circuit? All right, and let me get rid of these numbers here real quick. And so now we have 2 more vocabulary terms popping up in this question, path and circuit. All right, a path is any route through our graph that starts at one point and ends at another. So for instance, if I were to travel from F to H, right, so F to C to G to D to H, I started at F and I ended at H. That is a path. Okay. A circuit starts in one place and ends at that same place. So if I wanted to make this a circuit, I would have to return home, right? I'd have to return back to F somehow. So I could complete the circuit by going from H to A to E to B to back to F. All right, so now that would be a circuit because I started at F, traveled through my graph, and returned back to F. Okay. So now this last question is a little bit more of a challenge. They want us to find a circuit under certain conditions. And the conditions are that they want us to use every single edge exactly once. Right? So if you run into a question like this, my recommendation to you is to either print out these notes or draw this graph on your own and grab a highlighter and just start working your way through the graph. And remember, you can use every edge exactly once. So once you've used an edge, you cannot use it again. All right, so I'm going to start my circuit at F here in the upper left-hand corner, and I'm just going to travel. I'm going to start my travel. So I'm going to go from F to B. All right, and as I start making my circuit here, I want to make sure that I write my circuit down. So I started at F, and I went to B. Okay, and go back to my highlighter, and then from B, I went to E. Right, and you could have gone to A. Right, there's many ways to do this. I'm just making a circuit. You'll find your own circuit. Okay, so I went from F to B and then from B to E, and now that I've traveled these 2 edges, I cannot use them again. I cannot use these to return back to F. All right, so now that I'm at E, I only have one option here. I have to go down to A. There's only one edge for me to travel. Okay, and then so I went F, B, E, A. Before I get too far ahead of myself here, I'm going to write that down. All right, so I went F, B, E, A. All right, and then from A, I'm going to go to H. Let me grab my highlighter here. So I'm going to go to H. All right, I'm just highlighting my edges as I use them, so I'm not tempted to use them again. And then I'm going to go from H to D. Grab my pen, I'm going to write that down. So went F, B, E, A, H, D. All right, and then from D, I'm going to go to G and then to C. So grab my highlighter again. So I go G, C. Okay. Now here's the thing. This is where you got to get a little bit strategical, right? If I travel back up to F, I'm going to be trapped there because I don't have any edges that I will be able to use again. So I'm going to have to start taking care of these inside edges. So from C, I'm going to go to B. And I'm going to make sure I write that down again before I get too far ahead of myself. Okay, so I went from D, G, C, B. Right, so G to C to B. And then from B, I only have one option. There's only one edge I haven't used, so I got to go from B to A. And then once I'm at A, I only have one option, so I have to go from A to D. And then once I'm at D, I only have one option. I have to go back to C. Okay, so let me write those down. Okay, so I went from B to A to D back to C, so A, D, C here. And then once I'm at C, I only have one option. I have to go back up to F and return home, and that completes my circuit. And it uses every edge, right? I used every edge. Every edge is highlighted, and I only used it once. And this would be the circuit that does that. Okay, so kind of a challenge, right? You really have to know your vocabulary, and you really have to kind of keep track of things here. So organization is going to be key in these problems, and coming up with a systematic way for you to go through these graphs and making sure that you're labeling things as you go is going to be essential for your success here. Okay. All right. So let's take a look at that classical math problem. This was the problem that started it all, actually. So 300 years ago, back in the 18th century, this guy named Leonhard Euler was reading at the time what you would call a magazine or a journal. All right, and the mayor of this city, Königsberg here, posed a problem that he challenged people to try and solve. All right, so in Königsberg, they have this river, it runs through the cities, and these green things that I put in here, these are bridges. Okay, and what the people of Königsberg used to do is they used to try and walk across all these bridges. They wanted to walk across each bridge exactly once and start and stop in the same place. All right, and why they made this a challenge, I don't really know, but they found it fun. And Leonhard Euler, this guy right here, found it especially fun. And not only did he solve the problem that the mayor put in this magazine, he used this problem to spawn an entire field of mathematics that literally changed the world. All right, and I can't explain to you how important Leonhard Euler is to our world and how important he is to mathematics. This guy is like the Michael Jordan of mathematics, if that puts it in perspective for you. Okay, this guy is an actual genius. All right, so let me show you what he did here. All right, so Leonhard Euler, what he did was he looked at this map that was that the mayor gave everyone to try and solve this problem, and he said, okay, see all these different land masses? I'm going to shrink those down to a single point. So this land mass up here, right, this entire land mass, he just shrunk that down to a single point and called it a vertex. He said, here's a vertex. This vertex, we'll call it A, represents this entire land mass up here. Then we have this land mass here in the middle. Right, you see that entire island thing going on there? He's like, I'm going to draw that over here. I'm going to reduce that down to a single point. We'll call it B. All right, and then we have this land mass over here. All right, so this, and we'll reduce that down to a single point, and we'll call it C. Put that right there. All right, and then we have one more landmass, and that's this down here. We call these landmasses, right, because it's separated by water. All right, so these landmass, this landmass down here, we'll shrink that down to a single point, and we'll call it D. All right. Now, you guys know what edges are, right? So what do you think Euler let the edges represent? If you said bridges, well, that would be correct, right? So we have our bridges here that connect these different land masses, right? So if I'm looking at A, B, C, and D, let me get rid of all those squigglies so it's a little bit more clear here. Right. So there's our different land masses. You'll see that B and A are connected here by this bridge, right? So Euler came over here to his graph and he drew an edge connecting A and B. Now, cool thing about graph theory is that these edges, they don't have to be straight. You can curve them if you want. All right, all they do is they represent a connection. All right, there's another bridge that goes from B to A right here. All right, so I'm going to draw another edge going from B to A like that. Okay, now B to D, right, there is a bridge that goes from B to D here, so I'm going to draw in an edge going from B to D. And there's another bridge that goes from B to D right over here, right? So there's another one right there. So I'm going to draw in another edge going from B to D. How about going from B to C? Well, of course, there's a bridge right here. So I'm going to go from B to C. How about, can we get from C to A? And we can. There's a bridge right here. So I'll connect those two. And then there's a bridge down here that connects C and D. we go. So he took this entire city and all of its bridges and he reduced it to this graph. All right, and then he began analyzing it and essentially gave birth to graph theory. It's pretty crazy that this one puzzle spawned this entire thing. All right, so anyways, here we go. So we've got a graph, and the first question we want to know is how many vertices are there? Well, there's 1, 2, 3, 4 vertices, and then it wants to know the degree of each vertex. Right, so let's just list them out here. We got A, B, C, and D. Right, and if I look at vertex A, there's 1, 2, 3 vertices there. Or I'm sorry, 3 edges, right? So it's got a degree of 3. Right, if I look at vertex B, I got 1, 2, 3, 4, 5 edges coming into vertex B, so it's got a degree of 5. C has 1, 2, 3, so it's got a degree of 3. And D, 1, 2, 3, also has a degree of 3. Okay. Now the challenge here is, can you find a circuit that starts and ends at the same place and visits every landmass once? Not exactly what the citizens of Königsberg were trying to do, but this is much easier than trying to use every bridge exactly once. Okay, so I'm gonna grab my highlighter, and let's say we start at landmass A. We're gonna start here at landmass A, and our goal is to visit every landmass. Okay, so we want to visit every vertex on this graph exactly once. All right. Once we visit a vertex, we do not want to visit it again unless we are returning home. Okay, so we're going to start at vertex A. So we're starting here, and let's say we go to vertex B. All right, so we have a bridge there that we travel, and now B has been visited. And then let's say I go ahead and head down to vertex D. Okay, so we use that bridge right there to get down to vertex D. And then we're going to, so now that we visited A, B, and C, or A, B, and D, the only vertex left to visit is vertex C. So we'll come over here to vertex C. Now we visited vertex C. I cannot go back to B. I've already visited B, so I have to return home. So I'm going to return home to vertex A. There's my circuit, right? Because I started and stopped in the same place. I visited every vertex exactly once. And now I just need to write down that circuit. So I'm going to grab my pen. And let's see if we can write this thing down here. Okay, so we started at A. We traveled to B next. Then we went down to D. All right, so we went A, B, D. And then we went over to C. And then back to A. There's my circuit. All right. There we go. So that should be a good introduction to the 1 million vocabulary terms that we have to start off this unit and get you a little bit familiar with this stuff. And like I said, it's just an intro, so make sure you read through those definitions, try the practice problems, and get yourself acquainted with some of these new things. All right. If you have questions, let me know in the Zoom chat. All right. Have a great day, guys.